Hello all and welcome. Thank you for finding time to attend today's webinar. The particle size paradox. Is there a single best particle size technique? I'm Tony Thornton, the Director of Technical Information at Micromeritics Instrument Corporation, a global leader in material characterization technology. I will be your moderator today. Now, before we start, I want to provide some guidance on the format of today's event. First, attendees are in listen-only or muted mode during the presentation. If you have any questions on the content presented, click on the speech bubble with the question mark on the GoToWebinar dashboard. Type them in the chat box, and we will try to address them in the question and answer session at the end of the webinar. Only the organizers of the webinar will see the questions, and I will be monitoring them during the presentation, and then we will address what we can at the end. Note that for those that we do not address here, one of our team will provide you with an answer in the coming days after the webinar. Now, the webinar is being recorded, and the recording will be available on our web page landing page. Make sure you check back in around 1 week. You will also be provided a link to the recorded webinar via email once available, so keep an eye on your inbox for the availability of the recording and the link to it. Okay, let's get started. I am pleased to introduce today's speaker, Jack Saad, the Global Technical Training and Support Manager for Micromeritics, who received an ACS certified BS in chemistry from the University of Georgia here in the USA. Now, most of Jack's early career was spent in the pharmaceutical quality control. He joined Micromeritics in 2011 as a particle size application specialist. Now, please bear, and you see here his contact information, jack.saad@micromeritics.com. Now, if you will bear with me here for a moment, I am going to pass this over to Jack so that we can learn more about the particle size paradox. Is there a best particle size technique? Okay, Jack.
Thank you for the introduction. Again, my name is Jack Saad. I'm a member of the scientific staff at Micromeritics. Today I'll be talking about the particle size paradox. So I'd like to begin with an overview of this talk. We'll begin with why particle size. So why are we making these measurements? What are we doing with the data? And what are we trying to understand about our material? Then we'll look at an overview of different particle sizing techniques. How are they making the measurement, and what exactly are they measuring and converting into particle size? Start with a dynamic image analysis, then sedimentation analysis, static light scattering, or more commonly known as laser diffraction, electrical sensing zone, air permeability, and dynamic light scattering. Then we'll go over some case study data where we took some different materials with different shapes, and we analyzed them on multiple techniques, using multiple techniques, and compare the data. We'll then discuss how do we choose a technique and give you some insight into which techniques are appropriate for which applications, and then provide some concluding statements towards the end. So why are we measuring particle size? What information are we looking for? Are we trying to understand something about the behavior of the bulk material within a process? Are we looking for something like the individual particles after a process, like grinding or milling or precipitating? Are we looking at the effectiveness of a cleaning process or a recovery process? Is particle concentration important? Are we looking at the different layers of sediments? Or about solubility of the particles? Monitoring a change in the particle, like dissolving or dissolution or something like this, or another criteria or characteristic that would characterize your material or a process. Are aggregates and agglomerates present in your material? This is important because aggregates and agglomerates will give you information on the process or the behavior of the bulk material within a process. So when you're considering sample preparation for any of these techniques, It's important to note if these aggregates or agglomerates are there. And if they're there and you want to break them apart to get to the individual particles, you may need to add some additional energy like sonication or stirring, or maybe add some surfactants or surface modifying agents to the dispersion to try to break these particles apart. However, you also want to be careful not to fracture the particles. You don't want to put too much energy in the form of sonication or mixing to fracture the particles, because at that point you're artificially grinding them, and your particle size results may not actually represent the material or give you the information you need about your process. Other factors to consider is that particle sizing techniques typically report things in terms of equivalent spherical diameter. Many particulate systems contain particles of irregular shapes, and in most cases, various shapes can be found within one system. Things like silica, wollastonite, and kaolinite. You can see in the images here that there's a variety of different shapes, aspect ratios. In the kaolinite, you have also different colors and different sizes present in the same sample. Once you've understood what your needs are in terms of particle size, and you've taken into account the considerations that I just discussed, we have all these techniques available to us, and we have a particle and we want to measure the size. So the million-dollar question that I typically get is, which one gives you the answer? Which technique should I choose? The correct answer is that all of them give you the correct answer. These values that are produced by these different techniques may not be the same. They're all different. However, they're all correct. And that is why we call this the particle size paradox, is that each one of these techniques will give you a different answer, and all those answers are correct. All of these techniques measure some aspect of the particles, and they convert that value into a particle size using some kind of calculation. With dynamic image analysis, we're using various shape factors and definitions, and it assigns a numeric value related to how well that particle shape meets that shape definition. With sedimentation, we're using Stokes' law, and we're calculating the rate of change in absorbance as particles settle due to gravity. With laser diffraction, we're using me theory, and we're actually measuring angle and intensity of the scattered light from the particles. With electrical sensing zone, we're using the Coulter principle, and we're actually measuring electrical resistance that's proportional to the particle size. With air permeability, we're using the Cosini-Kármán equation, and we're looking at difference in air pressure as air passes through the particle bed. With dynamic light scattering, we're using Stokes-Einstein equation and monitoring Brownian motion, looking for fluctuations in scattered light over a time period. To get into more detail of these different techniques, I'll start with dynamic image analysis. Again, with dynamic image analysis, we're looking at different shape factors and calculating some linear dimension from the images captured by a camera. The sample or the material circulates through a cell, and we have a camera and a light source, and it's capturing images of the particles, and these images are stored in a computer and processed by the software, and applies different shape factors to give different values. These shape definitions are circular, ellipse, rectangular, polygon, fiber, irregular shapes, plus the ability to correlate any two using the Pearson coefficient. With sedimentation analysis, we're measuring the terminal velocity of the particles as they're settling through a liquid, and we're using the Stokes' law to make the calculation. The idea is that larger particles will settle fast, while the smaller particles will settle more slowly. We determine the settling velocity by looking at the X-ray absorbance and the rate of change of the X-ray absorbance of the material. And once we have that terminal velocity, we use Stokes' law, and we know the viscosity of the liquid, and we know the density of the suspending liquid, and we know the density of the particle, and we know the accelerating force, in this case gravity, we can determine the spherical diameter. So again, it's spherical. So for non-spherical particles, we redefine this definition of diameter to be the diameter of a sphere of the same material that has the same settling velocity as that of the measured particle, or the equivalent spherical diameter by sedimentation, or Stokes diameter. With particle size by static light scattering, or laser diffraction, we're looking at the interaction of laser light with particles, and how those particles scatter light at different angles and with different intensities. And we use me theory to make this calculation. The calculation for me theory is looking at intensity as a function of the angle. So it's the intensity of the scattered light as a function of the angle of the scattered light, and we're looking for these different scattering functions, lowercase I sub 1 of theta, I sub 2 of theta, are scattering functions. And these scattering functions, the more you collect of these, the more you get a distribution of different intensities. And from the distribution of different intensities, we can then calculate a radius from the different intensities. So each one of these scattering functions will give us a different radius. And once we collect the entire scattering pattern, we can collect a distribution of radii, or double it and you have the diameters. To give you some additional insight into this phenomenon, we're going to graph the angle theta on the x-axis versus the intensity I on the y-axis. The graph in the center is going to be the mixture of all the different components, while the side graphs are going to be all the individual components. And what you should expect to see is that the larger particles, the 340.5, will start to scatter light at lower angles, while the scattering intensity from the or the scattering from the smaller particles, the 4.54, will occur at the larger angles. So as you see this graph progressing, you start to see scattering from the large particles first, and then as it progresses, you'll see the scattering pattern occur from the smaller particles. And the smallest particles, it takes a little bit longer to catch all of those. As you can see, it's progressing. It's important to note the assumption made by laser diffraction is that the particles are spherical and isotropic, meaning that they have a nice smooth surface. For non-spherical particles, we have to redefine this definition to be a diameter of a sphere of the same material that produces a scattering pattern that best fits the measured scattering pattern, or equivalent spherical scattering diameter, or me diameter. Now, I want to review this again, or repeat this. We're looking at a scattering pattern, and we're trying to get that scattering pattern to best fit the measured scattering pattern. So we're looking at a model. We're not calculating particle size directly from the scattering pattern. We're calculating the sizes from a model, and that model has to fit the scattering pattern that is collected. So on the reports, you'll typically see something called a residual, which is how well the model fits the scattering pattern. This takes into account things like, if you have multiple refractive indices in the particular system, or different shapes, it'll all calculate to be equivalent spheres of the same material, of the same refractive index, and we're trying to get that to fit the model, and the results are calculated from the model. The next technique for particle sizing is electrical sensing zone. This technique is mature. It involves two cells of electrolyte separated by an insulating barrier, and you have a cylindrical orifice connecting the two, and you have electrodes in the one cell and the other cell, and as the liquid passes through the orifice, or the electrolyte passes through the orifice, it maintains a circuit, and if a particle passes through that opening, then it'll behave as a resistance to that circuit. This technique is based on the Coulter principle, and again, we're monitoring the resistance. The resistance you can see over on the right here in this animation. As the liquid electrolyte passes through the orifice, there's no resistance, but as a particle passes through, it behaves as a resistance, and the resistance, the amount of the resistance, is proportional to the volume displaced by the particle. As a larger particle passes through, you have a larger resistance. And what we're calculating is the change in the cross-sectional area based on the Coulter principle. Just like the previous technique, electrical sensing zone also assumes a spherical diameter. So when we deal with something that's not spherical, we have to redefine the definition of the size as the diameter of a sphere of the same material that produces the same electrical resistance as that of the measured particle, or equivalent spherical ESZ diameter or Coulter diameter. Now, remember, the resistance is caused by the volume of electrolyte displaced by the particle. So keep that in mind as we start looking at some of the case study data. The next technique for particle size is by air permeability. In air permeability, we have a packed powder bed and we're passing air through it, and as the air enters the powder bed, we're monitoring the air pressure, and when the air exits the powder bed, we're also monitoring the pressure of the exit, and we're looking at a pressure difference, and from that pressure difference we can calculate something about the particles. This technique is very mature. It's been around for quite some time. The original device that did this measurement is the Fisher 95 subsynthesizer. It has been since obsoleted, and of course you can see in this diagram or this image that it's here it's made out of wood. Of course there's more modern techniques now that are made out of metal and use a touch screen to make the same type of measurement. We use the Cosini-Kármán equation with air permeability to calculate the specific surface area first, knowing these different parameters about the material in the cell. Looking at this equation a little bit closer, again, if we know the cylinder length containing the material, we know the cylinder diameter, and we know the density of the particles, we can calculate this volume porosity of the powder bed, epsilon. It's a dimensionless value, and what we're actually looking for is the volume of the space in between the particles. So we're subtracting out the volume of the particles in that powder bed. And once we have that volume space or volume porosity, we use that in the Cosini-Kármán equation to calculate the surface area. Once we have the surface area, it's a simple conversion. Again, knowing the density of the material, we can calculate an average particle diameter. Now this technique of air permeability only determines an average particle size. It does not calculate a size distribution. However, there is some applications and benefits where this is commonly used, and in some cases a standard. For one, it determines a bulk property of a powder, since you're dealing with a packed powder bed rather than individual particles. It's frequently used with high density materials like metal powders. There's some ASTM standards around this. The analysis is dry and non-destructive. It's a quick and simple measure of relative fineness of a material, especially if you're monitoring a manufacturing process or a grinding process or milling process or something like this. It can give you a quick answer. Very little sample preparation is needed. It's a traditional method. It's mature. It's been around for a while. And again, it's included in many ISO and ASTM standards for different materials. The next technique for particle sizing is dynamic light scattering, or DLS. It's commonly known also as photon correlation spectroscopy or quasi-elastic spectroscopy. In this technique, we have particles suspended in a liquid, and they're too small to settle out. So as they maintain floating around buoyancy in the liquid, molecules of the liquid are colliding with those particles. And those collisions are going to result in Brownian motion, which is the particles moving around randomly in that suspension. When we fire a laser at the sample and we look at the scattered light, we can look at fluctuations in that scattered light that correlate back to the Brownian motion, and we can calculate some additional information about the material. This is what Brownian motion looks like. The idea is that when the particles are relatively small, their Brownian motion is fast, and they cause a rapid fluctuation in the scattered light. When the particles are larger, the Brownian motion is slower, and the scattering fluctuation is much more moderate. So to kind of illustrate that, we can see here the scattering intensity and the fluctuations over time, and we monitor it over time. We can see that small particles have a very rapid fluctuation. So the space between the peaks and the valleys of the scattering fluctuation is much shorter. For larger particles, it's a more moderate fluctuation, where the distance between the peaks and the valleys and the scattering fluctuation is much greater. From the scattering fluctuation, we can calculate an autocorrelation function, or parallelogram as it's sometimes called, here on the right. This graph represents the correlation between the time delay on the x-axis in terms of tau, and the correlation coefficient on the y-axis in terms of G2 of tau. And using this calculation, this graph, we know where the intercept is, which is B, and we know where the baseline is, which is A. We know where it starts to deviate from correlation, where it goes from where it's flat at the top at 100% correlation in the peaks, and it starts to shift downward. The gradient indicates the polydispersity of the sample, and this calculation, we need to know the refractive index of the media. All the other variables are given by the instrument engineering, and we're calculating this decay constant to get the D, capital D, which is the diffusion coefficient. Once we have the diffusion coefficient, we can calculate the particle size or particle diameter using the Stokes-Einstein equation. So we know the Boltzmann constant, we know the temperature, we know the viscosity of the suspending liquid, and from that we can calculate what's called the hydrodynamic diameter. Now this is the diameter of the particle based on its movement in water. Hydro meaning water, dynamic meaning movement. So again, it's based on the diffusion of the particle. It's not the actual diameter of the particle that you would see under a microscope or under an SEM or TEM. Now theoretically, all of these techniques should give us a similar measurement for spherical particles if we adhere to all the limitations and constraints of the different techniques. However, real particulate systems seldom comply completely with this. So we decided to look at spherical particles, rod-shaped particles, and irregular-shaped particles, and make some measurements on some of the techniques that cover similar ranges. So we looked at dynamic image analysis, sedimentation analysis, and laser diffraction, as well as electrical sensing zone. All four of these cover similar ranges, so they kind of overlapped with these samples. So we wanted to see what actually happens and what kind of data do we actually see when we make these measurements. For the spherical shaped particles, we used glass spheres. These tend to show a lot of good agreement between the techniques. You can see here the D10, D50, D90, and the mode. If you look at sedimentation, however, it looks like it shows slightly smaller results for the distribution than the other three techniques. When we looked at images of these particles, we found that the glass spheres were not completely solid. They had some hollow cavities filled with air or some kind of gas, and we believe that this probably caused a density gradient where some particles may not have been settling as fast as they would have if they were completely solid. So if we looked at two of these particles, say the one on the right is a solid sphere and slightly smaller. The one on the left is larger in size, however, it contains an air pocket. And if we put these in a cylinder and watch them settle, they'll probably settle at the same rate, which would make the size calculated of that larger sphere on the left, it would give us the same size as the one on the right. So by sedimentation, the equivalent spherical diameter would be the same. We used garnet as the irregular shaped particles, and what we found was that the particle sizes started to shift from each other. You can see that the sedimentation and the electrical sensing zone showed slightly smaller particle sizes than dynamic image analysis and static light scattering. So with sedimentation, if the particle shape is irregular, this tends to cause a drag effect that slows down the terminal velocity during sedimentation analysis, yielding a smaller particle size in the calculation. So if we compare the irregular shaped particle with a sphere here, place into a graduated cylinder and allow them to settle, because of the shape of the particle, it's going to settle slower than it would if it was a sphere. So the equivalent spherical diameter would be the same as the smaller particle sphere on the right. When we're looking at electrical sensing zone, we're looking at a volume of the liquid or electrolyte displaced by the particle. So as the particle is moving through the orifice, it's going to calculate a smaller equivalent spherical diameter than that of the original particle that has higher aspect ratios. So for rod-shaped particles, we used a wollastonite, and we see there's a bigger difference in the particle size distributions. Again, the electrical sensing zone and sedimentation showed smaller sizes because of the cases that we discussed earlier with the irregular shaped particles. However, what's interesting here is the laser light scattering or laser diffraction showed multimodal distribution. Looking at the image of the wollastonite, we definitely see rod-shaped particles, and the flow path of a laser diffraction instrument allows for a tumbling effect where the two-dimensional face that's facing the laser of the particle could be as large as the length of the rod and as small as the circumference of the width of the rod. This high aspect ratio also calls for a range of spherical models to fit the measured scattering pattern, and the tumbling effect generates a multimodal distribution in static light scattering. Think of this as a visual perspective. As these rod-shaped particles are tumbling through the analysis cell in a laser diffraction instrument, the laser is seeing different orientations of the particle, and these different orientations of the particle scatter light in a variety of different ways, and these will equate to different spherical models of different spherical sizes. And as you try to fit them together, you end up with a broad distribution with multiple modes. So now we go back to the question, which technique do we choose? Which one was going to give us the information we need about our material? What are we really trying to understand about our material, and how do we get that information from these different techniques? Each one of these techniques has a reason for its existence. It's been used and maybe even standardized in different industries. to give specific information, and really it comes down to applications, and sometimes more than one technique is needed to completely characterize a material. Start with dynamic image analysis. With dynamic image analysis, any particle system or emulsion can be suspended in liquid where the particles are larger than 1 micron is the typical application. Its primary purpose is shape analysis. So from the shape analysis, from the different models, you can use a spherical or circular model and calculate a size distribution from that. With sedimentation analysis, any inorganic material in high concentration, typically soils, minerals, or fine metal powders, or any kind of application where the particles are going to be falling through some medium, whether it's a liquid or through air. This technique was originally designed to replace a manual method called Andreasen pipette, where you looked at particles settling through a cylinder. Again, it's high concentration slurries is the primary application area. Static light scattering or laser diffraction, any organic or inorganic particles or emulsions as small as a few nanometers up to a few millimeters. Typically, this is why this technique is so popular and so common, is because of the broad size range. It gives you a fast analysis and a quick check of a size distribution, and gives you the D10, D50, D90 rather quickly. Electrical sensing zone, it's designed mostly for small concentrations of organic or inorganic particles in an aqueous suspension, because we have to make an electrolyte. It could be sometimes in some, we can make some organic liquids or solvents electrolytic and use this type of technology. Again, it's primarily a particle counting technique and gives you concentration information. So it's primarily used for particle counting or concentration. However, because you know the size of the orifice and you know the size of the distributions, you can calculate, or using different orifices, you can calculate distributions from this. With air permeability, high density powders such as metal powders provides a quick check for relative fineness of a powder. Notice I'm saying powder rather than particles, and the reason why this technique is important is because it's a fast analysis of a bulk property of powders, because the primary value you're getting from it is the porosity of the powder bed and how air passes through the powder bed. So again, it's giving you a measure of a bulk property, but it's also reporting it in terms of particle size. With dynamic image analysis, any nano suspension of particles or emulsions smaller than 1 micron, typically it's included with zeta potential, which gives you a measure of stability of a suspension. Again, think of this as a particle suspension analyzer. It gives you some, again, some indication of how stable a suspension is in the submicron range, whether you're going to have separation or stable dispersion. To kind of conclude things, looking at all the data we presented and all the techniques and what they're measuring, simply converting measurements to equivalent spherical diameter is not necessarily sufficient to bring all the size determinations into agreement. Only in very limited cases can two different techniques, sizing techniques, be expected to agree. Therefore, when communicating particle size, the measurement technique is also an important quality to include. Furthermore, including information about particle shape is also advisable, particularly if the size data is to be compared to results from another technique, because the reported size is technique dependent. There is not a definitive particle sizing technique. With that, I'd like to thank you for your attention. I hope you found this webinar informative and helpful with your work and understanding particle size. If you have any questions, anything I didn't cover today, feel free to email me. My email address is here. For past or future webinars, please visit micromeritics.com/webinars. We also have online training, training modules covering different topics at micro.edu. Just
Okay, thank you very much, Jack. And thanks again to everyone for attending. And Jack, we've got a number of questions that we have received. I've been watching them as we've gone along. Some of them have been asked a couple of different ways and a couple of different times. So let me get the first one here for you. The first one, the air permeability sizing technique only reports an average size, not a distribution. If we have a laser diffraction unit that does report size distribution, why would anyone need an air permeability sizing instrument? And Jack, I don't hear you. Are you muted? Oh.
Can you hear me?
Again? Yes, yes.
Okay. Yeah, so this is a excuse me, good question. With the air permeability technique, as I mentioned, you do get the porosity of the powder bed, so it's also giving you a bulk property of a powder. In applications where you're trying to maybe pass some type of air or gas or something through the powder bed, in the case of maybe, for example, like explosives, you have some type of metal powder or gunpowder or something like this for like fireworks or ammunition or things like that, where you need to pass oxygen, through the powder bed in order to get the appropriate reaction. So how porous is that packed powder bed? How can you compact the powder in a way to get the optimal explosion? Of course, the particle size distribution is important, but how does air pass through that powder bed is also very important quality. So in that type of application, it's important to fully characterize the material based on the application and how it's being used. So you would probably need two devices. You'd need laser diffraction for the size distribution and an air permeability device to give you the bulk property of the powder and how you can compact it.
Okay, thank you, Jack. Here's another one, and we've got several related to this one. So we have a sedimentation instrument, but our customers have laser diffraction instruments. Is there a way to correlate the data?
I've been asked that question many times. Unfortunately, it's because of the way the instruments are measuring particle size, as you saw in the calculations that I showed, sedimentation, we're using Stokes' law, which is based on how the particle is moving through a liquid due to settling or sedimentation. With laser diffraction, we're using Me theory, which looks at angle and intensity of the scattered light. And because we're measuring two different aspects of the particles, there's no real good way to correlate anything unless you're working with exact spheres. If the particles are, perfect spheres and meet all the constraints, then yeah, you could probably correlate something. However, different materials, different shapes, different surfaces, how they scatter light versus how they settle through a liquid, all these different things will affect the measurement, and it'll be very difficult to try to find some type of correlation or detailed correlation. You may be able to get similar information if the particles are relatively fine or you have a large number of fines. Both techniques will demonstrate that. If there's a lot of coarse material or the presence of coarse material in the particle size distribution, both techniques will give you that information. However, to get the exact values to match would be very challenging.
Okay, great. Another really good question here, Jack. When looking at these more sophisticated techniques, how does particle sieving through different sized sieves compare?
I would say probably particle sieving has probably some of its own constraints, especially if you're working with irregular shaped particles or rod shaped particles, how they pass through the sieve based on spherical diameter. Because what you're looking for is how does a sphere fit through the square opening in the sieve. And depending on the orientation of the rod-shaped particles, how does it pass through? Are you really getting a true distribution? How does the aspect ratio affecting the results? It would probably be, comparable to sedimentation or laser diffraction. However, because of all the different constraints that are involved with sieving, it still would be somewhat of a challenge if you have some rod-shaped particles or maybe even irregular shaped particles, just how they interact with the sieve screening. But it's, I'd say, closer to laser diffraction or sedimentation.
Okay. Speaking of sedimentation, it says with sedimentation, is there not a maximum concentration of 1% or due to interaction of particles, so-called hindered settling?
There is a limitation. I think it's about 5%. With hindered settling, what you want the concentration to be so that you have a laminar flow around the particles. So as the particles are settling, the liquid goes around the particle and goes back to the way it was. If there's a turbulent flow, or if there's hindered settling where the particles are interacting with each other, or if, say, you have some very large particles that are crashing through smaller particles below it, it's going to cause some turbulence. You probably need to increase the viscosity of the liquid to an optimal viscosity that would carry those particles and slow down the settling enough to be monitored and not cause turbulence. So there's a number of factors that go into it, in addition to using surfactants and sample preparation to make sure you got a proper dispersion of the particles, so that you try to limit some of those interactions.
Mm-hmm. So primarily, just as long as we stay below about 5 volume percent, we should be good. That the one particle passing through the liquid doesn't influence another one. Okay.
No, that's correct.
Okay. Okay, another one here. Could you tell us the recommended technique to determine size of nanoparticles?
For nanoparticles, probably dynamic light scattering. That's based on primarily like the nano size range. I think the size range for that technique is usually just below 1 nanometer up to about 5 to 10 microns. The upper limit varies because we're looking for Brownian motion in that technique. And if the particles are too big, or the density is high enough of the particles, they'll start to settle more than they're in Brownian motion. And if they're settling, the instruments are not going to be able to basically make sense out of the results, because it's looking at scattered light due to settling and not Brownian motion, but it'll interpret it as Brownian motion and give some inconsistent results. So for nanoparticles, if it's less than 1 micron, dynamic light scattering is the best. However, with dynamic light scattering, if you have a dry material and you try to put it into a liquid, there's a lot of other considerations to take into account, because the particles at that point are so small that there's a lot of chemistry involved. So things like pH, types of surfactants, concentration of the surfactant, concentration of the particles, things like that will affect the Brownian motion. So there's a whole nother set of constraints, but typically if you're working with less than 1 micron, dynamic light scattering is probably the better technique.
Okay. There's a number of related questions here, and they all have to do with shape. So let me try to combine those in. And if you're doing particle size analysis, but your particles aren't, regardless of technique, and your particles are not spherical, what's the best way to determine aspect ratios or get information about, more related to the shape of the particle rather than just some interpreted particle size distribution?
The best way would be the dynamic shape analysis. With that, you saw like the list of definitions that we can apply and look at the different shape factors and calculate some values based on that, and be able to give some aspect ratio, some how irregular are the particles. And what's actually nice about that is that you can separate the data into two bins. So if you have a mixture of spherical particles and rod-shaped particles, and it's in a mixture, you can use dynamic image analysis, and once you have capture all the images of the particles, you can separate them in the software and look at only spherical particles, ignoring the rod-shaped ones, or you can look at the rod-shaped ones, ignoring anything spherical. With that, you can also get the aspect ratio, as well as ignoring the tumbling effect, that where the diameter of the width of the particle is being shown and shows up as a sphere. You can ignore those and look at how long the particle is, length versus width, in terms of that. So that's probably the better technique to use. If you have data from a laser instrument or sedimentation or any of the other techniques, and using that in conjunction with a shape analyzer, that will really give you something to really something powerful to characterize your material.
Okay. Back to, I hate to jump around on you like this. I'm receiving a lot of questions, folks. I appreciate this, and then I will remind you that for those we don't address here, we certainly will have someone in our team get back to you. But let's go back to dynamic light scattering, because I've seen this one a couple of times. You can have the reporting of Z average, volume average, number average, and intensity average particle sizes in terms of polymers, which are known to aggregate. Which is the most reliable output?
The most reliable output would be the Z average. The Z average and polydispersity index are the primary results mentioned in the ISO standard for dynamic light scattering. The intensity, well, theoretically, back in, I guess, in the older days when dynamic light scattering first came out, it's a type of spectroscopy. Sometimes it's even referred to as photon correlation spectroscopy. And you don't really get a distribution from it. You get, a few results. And with the Z average and the polydispersity index, that gives you the average size and the width of the distribution, or the variability in that size. As technology improves, detectors improve, lasers improve, computing power improves, processing power in the computers improves. We've been able to get more and more accurate distributions. However, the technique itself is inherently not a high resolution technique, because we're still looking for Brownian motion. And if you have 100 nanometer particles and 110 nanometer particles mixed together, most devices can't tell you the difference, because the Brownian motion looks so similar. So you can use intensity distributions, which is the primary output, again, from DLS. So I'd say, ranking in order of the best to the least, would be Z average, polydispersity index would be the best. Next would be the intensity distribution, because that's the primary output from DLS. And then volume and number distribution will probably bore towards the end, because you have to use the refractive index of the material to make that calculation from the intensity distribution. And if you're using the refractive index of the material, it's based on the wavelength of the laser, which is usually a red laser, around between 630 to 670 nanometers. But we're still talking about something that's a fraction of the size of the wavelength of the light. So it starts to become a situation where, how accurate is that calculation if the particle itself may not even interact with visible light? And also I forgot to mention that the technique is also based on Rayleigh scattering, not necessarily Mie scattering. So trying to force a Mie scattering model using the refractive index on those types of particles, leads to some inaccuracy. So again, Z average and polydispersity index are probably the best values to use.
Okay, thank you for resolving that question between the different average values from that technique. Some related questions are coming in here too. One was specific for flaked aluminum material. What's the best way to determine the thickness? But then there's a general question, will platelet-shaped particles tend to create bimodal results with laser diffraction instruments? So if we could kind of address both of those, what would be best? Should we expect to see bimodal distributions with flake or with the plate-shaped particles? And then when we do have plate-shaped particles, which is the best way to get insight to the thickness of those particles?
Yeah. So flake-like or plate-like shaped particles, with the laser diffraction, you probably would see a bimodal distribution, because you'd see the flat side, and then you'd see the where it's kind of flat against the laser, or the wider side, and then you also see the length, or the on the when you flip it 90 degrees, you'll see that side as well. So the laser will see both of those, and again, it's trying to force it into a spherical model. So it'll probably use two spherical models to make those results. That's what we saw with the wollastonite in the results that we showed in the case study. So combining maybe laser diffraction data with shape analysis, as I mentioned before, with the dynamic shape analysis, you can see both faces, and when you're using the software to say ignore the broad side and look at the narrow side, and you could get some thickness information there. We could also look at the flat side and see how wide it is, how it maybe stack, how it could stack and things like that. So using a combination of laser diffraction and dynamic shape analysis would be the best bet for plate-like materials.
Okay. A couple of questions relating to the primary topic, or the opening question of this this presentation.
Sure.
And I'll let me put them together basically in this form. Which would be the common accepted reference particle size distribution method?
The most common?
Well, it says, what would be the common accepted reference method? And I'm not sure there's an answer to that.
Yeah, there's not really an answer to that. One of the things that I pointed out, or tried to point out in this presentation, and really is the takeaway message from this, is that there are many particle sizing techniques. There's some that I didn't mention in this talk, and realistically, the correct method depends on the application, depends on how you're using your material. How is it being processed? What is the next step for that powder or those particles? If you're, something passing, if you have something where you're maybe putting particles through like some kind of like a hopper or a chute when it's flowing down, well, those particles are settling through air. So the settling motion, that settling, motion of the particles would be comparable to the sedimentation analysis. So maybe not necessarily like laser data may not give you the full picture on how they're going to settle. Likewise, if you're looking at concentration, electrical sensing zone would give you a concentration. If you're looking at a cleaning process or something is left over after a process or manufacturing process, if you're looking at shape, if you have different shape particles, shape analysis is important. If your application deals with some type of particle bed and fluidizing a particle bed, then air permeability would be a good technique to use. So it comes down to how are you using your material and which particle sizing technique kind of replicates the application. For example, like one of the common applications for the sedimentation analysis is soil analysis, because particles settle in the air and they stack, on top of each other in a way where you have maybe the heavier particles on the bottom and the smaller particles on top. So how does that settling affect in the air? Or if you're working on oceanography, how do the particles, how do the sediments separate in the ocean floor? Well, the sedimentation analysis is going to give you that direct representation. It's also used heavily in mining. So in mining applications, the sedimentation analysis is widely used. Part of it is because they used to use the old cylinder methods and the Andreessen pipette method, and sedimentation analysis now, is an automated process of that same technique. It gives comparable data. And as I mentioned, the air permeability technique, it's been around for a while. The Fisher sub-sieve sizer has been around for a while and written to a lot of standards for ISO and ASTM. So it's been around for quite a while for certain applications, certain areas, certain industries where it's important. So, and again, it just depends on the application. So think about your application, think about how your material is going to be used. And, the most common instrument out there, the most common technology, because of its broad range, is laser diffraction. However, complementing laser diffraction with one of these other techniques can sometimes give you more information about the material. In some cases, if you're just looking at D10, D50, D90 of the distribution from a laser instrument, you may get two lots of material that will give you the same results and pass the specifications that you set for it. However, the two lots may not behave the same way in the application or in the process where you're using them, and which leads to a mystery as to what's causing it. The distribution looks the same, D10, D50, D90 pass, they're all the same. What else can be used? Well, maybe it is one of these other techniques can give you that answer. Maybe the particle shapes are different. Maybe, the way the particles are interacting is different. It could be a whole host of different physical characteristics that can be measured by other devices to help complement the laser diffraction data. So, like I said, there's no right or wrong answer, and that's why, we call this particle size paradox, is because they're all giving you the right answer. It just depends on your application and how you're using the material that you're testing.
Okay, and I've got time probably for one last question before we wrap it up, and it's actually not specifically a particle size question, but I'll ask you, Jack, because it in a way it refers to a previous presentation you've already given. And that question is, what is the value of a technique such as BET, and how would it compare to these techniques?
Oh, well, yeah, that was the previous webinar that I think I gave on surface area. BET gives you really detailed information of the surface of the particles. So it'll give you, for materials that are really, really small, particles or powders that are really small, BET will give you the surface area, which is the most detailed. And you can even use that surface area data to calculate particle size if you know the density. If your particles are spherical, like perfect spheres, with no surface features at all, we found that air permeability and laser diffraction and BET analysis all agree with each other. They'll be very close in value for size and for surface area calculation. But as you deviate from spheres, as you get a broader distribution of particle sizes, the BET result will give you more detail on the surface. So if your application involves some type of surface reaction or surface, something about the surface of the material is important, like a coating process or something like this, BET will give you really good results and give you the information that you need. Typically, laser diffraction and BET analysis are usually performed on the same material to kind of fully characterize it. In addition, you can use, I guess, like I said, any of these other techniques. And sometimes, if you don't have these techniques available in your lab, one thing I didn't mention either, if you don't have these instruments available in your lab at your disposal, you can also look for some contract labs. We have a contract lab here at Micromeritics particle testing authority, where we have all these technologies available. So if you have 2 lots or 3 lots of material that may not be behaving the same way, you've already done BET analysis, you've already done particle size analysis, and you want some additional testing using maybe a different particle sizing technique or some other characteristic like powder flow, things like that. We have those tests available for a small price, and can perform those tests and give you the results and help you see, determine which one's the most appropriate and what's causing problems with your process or the variation between the lots. So I just want to throw that out there as well. I guess that answered the question.
I think so.
All right.
That brings us to the end of our scheduled time here. Jack, thank you so much for the presentation and for answering these questions. Thank you to the attendees for attending, for taking the time today, and for your follow-up questions. Yes, there are a number we did not address here. We will get back with you. One of our team members will be back with you with answers to those shortly. As I mentioned earlier, this has been recorded today, and it will be posted on the Micromeritics webinar landing page, and each of you will receive via email a link to this. You see here an email address, general information or info@micromeritics.com. Also, don't forget you have Jack's email address, jack.saad@micromeritics.com, if you want to follow up with additional questions later. Again, thanks everyone for attending, and that will conclude our webinar for today. And I will say goodbye. Thank you.
Thank you.